Hello. Um, yep. So this is January the 18th. I want to continue where I was before. Yeah. On the previous journey, I read this article about understanding Apache Fluss from Jackman Lively. Uh, I just I record myself 1 hour and 44 minutes, but on the minute 20, I went to the bathroom and I forgot to unmute myself. So basically, the rest of the videos has no sound. So right now, I have made sure that my audio is working. Okay, so let's continue where we left before. Maybe I will try to reread some of the previous part. I might have forgot about some of the things. So let me review. Let me do some review. So firstly, we read about the Fluss cluster. Okay, the Fluss cluster core architecture, which is the zookeeper, the coordinator that does all the coordination in distributed system. There's a tablet server and that that actually store the streaming data, the whole data. Okay, yeah, I still remember that part. And then it has the internal tiering services. Yeah, tiering I forgot it. Does it tier only to object storage? And then there's also lakehouse part here. I don't know if it is done by the same tiering service or it is different. Okay, I can't remember that part. I think it's later will be, yeah, this one is without lake house, so probably it will be covered later on in the chapter. Log table. So okay, this one is what happened inside the tablet server. Okay, the log table, it contains partition, and yeah, I forgot the details why we have the bucket and stuff. Yeah, this one is partition basically. The log tablet is ordered by yeah, partition by basic column that you choose. Okay. Replication. Okay, it's bool based replication by the follower. Okay, it built on Kafka protocol. um it's similar to Kafka topic partition. By default, its log table has 3 replicas with 1 liter and 2 followers. Okay. um Columnar storage, yeah, using RO IPC. Yep, I remember this part. It cannot do projection push down on the, I forgot. Let me read this part. Fluss optionally stores log table pages in columnar format to allow for projection push down to the file system level. Okay. As well as obtaining the other benefits of Arrow. Fluss client accumulates record into batches and then serialize each batch into Arrow factors using Arrow IPC. Log tablet replicas append these Arrow IPC record patches to log segment file on disk as is. Okay, and these Arrow record patches are self-describing with metadata to allow file reader to be able to read only the requested column from this. Okay, projection pushdown consists of client including a column projection in its fetch request, and that projection getting pushed all the way down to the file storage level. That prunes unwanted columns while routing the data from disk. Again, normal projection push down. This avoids network I/O but come with additional I/O storage. Additional storage I/O overhead if columns of the projection are widely fragmented across file. Um, Yeah, I mean, is it one file only consists of single column? I have no idea how columnar format looks like, but how come one column fragmented across file? I have no idea. Storing log table as data, table data as a sequence of concatenated ROIPC record batches is quite different to using a single packet file as a segment file. Yeah, this one I have a question before. I still have a question. I haven't really take a look at it. A segment file with 100 concatenated ROIPC record batches store its paths as its own self-contained columnar block. Sorting a single column across the file requires touching every batch metadata in buffers, where a pocket file lays out column contiguously across the entire file, allowing track book column reads. Yeah, this is what I had before. The question um is arrow batches equal or works similarly with Parquet Parquet what is it Parquet row group, because this one is, if I understand correctly how Parquet works, this one Parquet lays out column contiguously across the entire file is not very true unless you create your row group as many records as available. Technically you use PEX packs, where uh it is, yeah, it groups each column like multiple different rows as a single group of columnar, so it's not really like the entire column getting smashed into like single part of the file. um yeah, that's what my understanding, so I don't really understand this part. I will have to take a look later. um but serializing patches into project file on finding also not a good idea. Yeah, I have no idea with what this works. So this RIPC file semantic on. This doesn't already explain why serializing patches into Parquet files on the client is not a really good idea. Why? Why? Yeah, I had the question before. On the consumption side, plus clients convert the arrow vectors back into rows. This columnar storage is entirely abstracted away from application codes. Okay. Let me read this part. I really want to understand Parquet files and okay, let's move on. Yeah, log record which change type. Yeah, basically every row, every change, every event create a change type. What happens to the the table? Is it being appended? Is it being updated? Is it being inserted? Is it being deleted? So it's like I didn't, probably could be like uh metadata on the event itself. Yeah, for all table, the Fluss client assign its record the A plus change type, because yeah, it's append only. The log table is append only, while the remaining change type are used for change log of PK primary key tables, which is explained in the PK table section. Yeah, like how steering. Yeah, Fluss has the type of tiering, internal tiering, akin to a traditional tiered storage, which is covered in the section. Like how steering. Yeah. Next section. Tablet server internally tier log tablet segment files to object storage, which matches the general approach of Kafka. Kafka latest, uh, I think this one is quite new. The tiering things. Yeah, not very new, but it is somewhat introduced not very long time ago. The difference is that when Fluss client fetches from offset that is tiered, the log tables return only the metadata of a set data of a set of tiered log segments, so that Fluss client can download the segment itself. This offloads load from Fluss server during catch-up reads. Yeah, so basically, yeah, if when someone the client asks the log table, hey, I want this offsets. Oh, sorry, we don't know, we don't have that, so it must be in the object storage. Here you go, the address, the byte starts. I don't know what kind of file message that you can provide when fetching when you want to fetch some a particular section of the your files on S3. You can provide that. Basically, the log table that will only give that, and the Fluss client just download that for themselves. So yeah, the log tablet is not really getting overhead by downloading the data for the client, which I think it's like I don't know, I think this design trade-off it's really like intentional. I don't know what kind of system that they are building that that it's very. I feel like basically before this reading I have watched the video from the author of the Apache Fluss, uh, mentioned quite a lot about the what's it catch up reads basically like backfilling. It mentioned quite a lot. I think it was intentional that the in Alibaba probably there are a lot of this kind of use cases. So maybe this is first class citizen to be able to catch up quickly. Uh, and 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 I don't know, the Fluss probably like the Fluss is kind of centralized, and there's a lot of client that needs to be able to catch up with to do the backfilling. That's why it doesn't really want to overload the log tablet server. Maybe that's yeah. This sounds very intentional because I personally like the idea of abstracting away the the whatever that makes the interface simpler. Basically, this way the trade-off makes sense. I mean, the trade-off makes sense, but then you have to expose your object storage and the lake house later on. There's a lake house to the client, which is means client knows quite a lot of things. Yeah, this is quite interesting design choice. Uh, yeah, this one. Plus made the decision to place some logic on the client for merging local data on the tablet server. This with internally tiered data on storage. This diverge from Kafka API, which does not support it, placing the burden of downloading segment on the Kafka broker, which yeah, I just mentioned about this. The actual tiering work is performed as follows. Each table server has a remote log manager, which is responsible for tiering segment to the remote storage via log tiering tasks. Oh yeah, yeah. By the way, I also read about this before. Oh, not my first streaming. The log manager is is um is a playing job, if I'm not wrong. Is it so? I forgot. There's certain job. Let me continue reading this, which is responsible for tiering segments to remote storage, the object storage, via log tiering tasks. The remote log can only trigger tiering tasks for log tablets that have their later replicas on this server. Each tiering type its steering path works as follows. A task scope to the single tablet, identify local segment file to upload and remote ones to export based on TTL. It uploads target segment of storage, commits them by creating new manifest file, blah blah blah. Write the manifest file to update storage. So create the manifest file of our current remote segment. Write the manifest file to update storage. Send a commit log manifest request to coordinator which contains the path to the manifest file in remote storage. The coordinator should not store the manifest itself. Okay. Once committed, expired segment files are deleted. Sorry, what is segment file? What does it look like? I forgot. What is segment file? This one. Tablet server internally tier log tablet segment file. Sorry, I forgot what segment is. This one segment. Oh yeah, this one. Okay. Yeah, segment is basically the smallest part of the log tablet. Tablet. Okay. Once committed, the segment files are deleted in the expired segment file deleted. Asynchronously, the coordinator notifies the log tablet's replica via okay, blah blah blah. I've read this part. Yeah, let's skip this part. I still remember this part. Okay, let me reread this part. Primary key tables. A primary key table is also organized into two logical level of partition. Okay. Two logical level of partitions and table buckets. Clients write data to specific partition. Okay, like Kafka. And buckets are described in the log tablet section. Yeah, it's before. It's above. However, the primary key table has a different API as it is mutable table. Mutable. Write, observe, and deletes to the table via put a kv API. Reads, lookup, and prefix lookup against the table. And changelog scans, which can involve a hybrid read of kv snapshot files plus changelog discussed later. Each table bucket of a PK table is backed by a kv tablet, which is RocksDB, which emits changes to a child log tablet. Why there's a child? Oh, child is the follower, is it? Or is it different? Kv, is it? I mean, it's different, but is it the same concept? Kv tablet state is composed of RocksDB for storing the key table, yeah, the content itself, and a log tablet for storing the changelog, which is where's this one, the log tablet. This inner log tablet also acts as write ahead log, as described in the writing to KV section. Yeah, this one is below. I want to know if log tablet is, I mean, is it something that the child tablet can control? Because this one is fetch. That means the inner log tablet acts as write ahead log. Is the which one is the inner? This one. Child log tablet is the inner. Okay. Log tablet for storing changelog. The inner log tablet. The leader, basically, yeah. Unlike log tablets, KV tablet do not store the data in a raw format, as the data is stored in RocksDB. However, the child log tablet uses arrow as normal. There are a few other notable differences to log tablets in how data is returned, tiered, and read, which is covered in next subsection. Quite interesting. So internally it works quite different. Yeah, because it is immutable data storage. Yeah, it's understandable. It's going to be more complicated. Okay, so let's actually continue my part. Writing to KV tablet and understanding durability. The put KV API accepts a KV batch which contains a set of key value records. Okay, so it's not it accepts batch, but I think it also can accept a single key write, right? When the value is not null, Fluss treats this as an observed, and when the value is null, it treats it as a delete. Okay, that's normal. The KV tablet performs the write as follows. First, record in the batch, perform reads against RocksDB to RocksDB table to determine the change to be emitted to the change log. Wait, where's the change log? Is it the log tablet is the change log? Yep, yeah. The KV is the actual data and the change log is in the log. Okay. A record could be a delete record with the old row if the write contains a null value, an update before record with the original record, and an update after record with the new record if a record exists and the write has no null value, an insert with new record if no existing record exists. Buffer both the new change log records and the RocksDB write in memory for now. Why the RocksDB write in memory? Why it does not immediately being committed by the RocksDB? Append all buffer changelog records. Append all buffer changelog records, which is this one, right? In memory, basically, yeah, the buffer as an RIPC record batch to the child log tablet and wait for the batch to get committed based on Kafka protocol. So to the child log tablet. So this one. Oh man, I know this. I was reading this as if the first entry is this one. Actually, yeah, I should have read this one. Put KV is here, and then it's going to append to the chat log, and it's going to be replicated by this follower, and then yeah, that's about it. And when after this one completely replicate the data from this chat log, and the who is going to commit once the once you get committed, yeah, based on replication Kafka replication protocol. Okay, once the change records are committed, perform the buffer RocksDB writes. Okay. Oh, okay, it's not immediately can commit. The new records override the existing record by default, but with a merge engine and partial updates in the next section. The new record override the existing record by default. New record. I mean, yeah, you it accept whatever the value or the record being written the last. Yeah, this is not very new. Okay, it's understandable. So it buffer here. So when a key or value is being written to here, First it writes to the RockDB, not yet committed, and it appends the chat logs and wait the chat log to writes the chat log and wait for the log tablet to replicate it, and once it said, hey, yeah, we have committed it, and notify how to notify it, maybe this one. Append. So I suppose that all of this write is synchronous, so it can be like one way here, write a chat and being replicated. I responded, okay, it has committed, so it will respond to here, and hey, I have committed, and Roxy be going to be say, okay, let's commit this whatever we have in the memory. Okay, quite a lot of write path, but yeah, that's how it works with the distributed system. So durability, a log tablet is like Kafka partition. It is replicated across multiple servers with one leader and multiple followers. The KV tablet itself, this one is unreplicated. So it does regularly upload RockDB snapshot files to object storage. It's unreplicated. I mean, why would you replicate this one? It's literally here. I mean, this one is just the pen. This is log. I assume it's like a pen only log. So it's like write ahead log, right? So you technically do not need to replicate this one. If it crashes somehow, yeah, you can just pull whatever the write ahead logs has and rebuild it, so it doesn't really need to be replicated. Therefore, the changelog as yeah, this is what I just said. The changelog acts as a replicated write ahead log for the KV tablet. If the server disk were to die, the state could be recovered by downloading the latest KV tablet snapshot file and replaying the changelog from the corresponding next offset. Last offset is stored with the snapshot again. Interestingly, the KV tablet leader has no follower and moves with the log tablet leader. You mean this one? This leader move within. Okay. When a leader election occurs in the log tablet, the KV tablet leader changes with it. The new KV tablet leader on the tablet server or the new log tablet leader must download the latest RocksDB snapshot file and replay the changelog to recover the state of the former KV leader. This means that large RocksDB state could be an issue for availability due to the large amount of state needing to be downloaded and replayed on its leader election. This design may change in the future. Yeah, this is not very ideal. Yeah, this is not very ideal. Okay, I understand why. Why don't they just can they rebuild the RocksDB state from the write log itself? I don't know. It should be, right? It should be. If you regularly compact this, I don't know. Yeah, if you regularly like have a certain compacted data, you can easily rebuild the RocksDB state. Probably. Yeah, okay. Merge engine and partial update. By default, PK tables have no merge engine. The new row overrides the old row via the default row merger class, as described in the last subsection. But Fluss supports using the merge type first row and version it in picky tables. Each merge operation has an old row and a new row, either of which could be a null. Merge type none. New row replace old row. First row keep the old row unless it null. Then take the new row. Okay. Version take whichever row has highest version. The new row version is supplied by the client. Why? Why is it supplied by the client? Normally, row version is like being atomically incremented on the server. I don't know why it's supplied by client. The flame source for Fluss can use first row, but version doesn't seem to be used anywhere yet. Okay, partial update. An update does not need to include all columns. Okay. Allowing for partial updates. Okay, so you can update certain column only. Partial updates cannot be combined with merge type if a write only contain a subset of the column. The partial update row merger class is used instead of default merger class. It goes column by column and takes the column from the new row. If it exists, else take it from the old row to create the new merged row. Yeah, I don't really care about this particular logic. Key tablet tiering. The keyed state in RocksDB cannot be tiered. It must be fit entirely on disk. Snapshots are made and stored in object storage, but this is not tiering. But for backup, recovery, and historical reads. Therefore, a key cardinality should not be excessive. The changelog is log tablet and is tiered as described in the log table tiering subsection. Okay. Yeah, it makes sense. Put KV. So the Fluss from the client. Put KV with observer GUID to the KV tablet. Going to be copied. Written to the RocksDB. RocksDB snapshot file. Snapshot file is like copying the whole file. The changes are going to be. This is the child log tablets. Yeah. This is the write-ahead logs, and then tablet server. Okay, this is this dashes is the tablet server. It's going to be replicated. Oh, sorry, tiered to the object storage. Okay, and then this one. What is this? This is the log. This is the Kafka replication stuff. Okay, and what is this? Fluss client CDC stream reader. Oh, okay. So this one going to read from the write-ahead log directly, and it can download the segment from the object storage directly. So yeah, it happens when the catch up or the backfilling stuff. And also download RocksDB snapshot file, historical reads. I don't know why the Fluss client needs the RocksDB part. I thought this one is only for this replication. Okay, I don't know. I'm not aware of this one. Scanning a KV tablet for changelog. A Fluss client can send lookup and prefix lookup request to the KV tablet reader, which is this, which gets translated into RocksDB lookup, and prefix lookup. Yeah, basically point lookup in the RocksDB in the KV. It is also possible to scan the changelog, and there are different options from the starting offset here. So scan the changelog is this one. Why would you want to do that? Earliest offset, read the entire change stream from start to finish, assuming the infinite retention of the log tablet. Latest offset, read only the latest changes from the log tablet, but will miss historical data. Full bootstrap. Oh, bootstrap from table RocksDB snapshot, then switch over to reading from log tablet. Oh, I see. This is this part. Why it needs to copy the whole thing, because it is easier. Yeah, just copy the whole thing. Okay, makes sense. When using the full mode, the process works as follows. The Fluss client contacts the coordinator server to find out the KV snapshot file. Why is it files? Is it going to download multiple RocksDB files? I don't know. Along with the changelog offset by they correspond to. I don't really understand this one. So you can have different RocksDB segment for different changelog offset. Fluss client downloads the RocksDB snapshot file and initializes a RocksDB instance based on the files. Okay. Fluss client iterates over the record of the RocksDB table, treating each record as an insert row kind. Fluss client switches to reading the from the log tablet directly, starting from the next offset after the snapshot. This follows the same logic with the log tablet, where the client may not receive the actual patches, but metadata is cleared log segment. Oh, okay. Oh, sorry. The same logic as log tablet. I forgot about this one. Log tablet. I always thought this one, this part, downloading from object storage partially and downloading from the log tablet partially is always Fluss client. I'm not aware that this is also used internally. Okay, that's interesting. So I mean, like, so that means if let's take a look. If there is a log tablet, see, I'm aware of this part where the client could download from the object store directly, but log tablet. Wait. This is log tablet. Oh, okay. So it is referring. Oh, okay. So I understand this. So the Fluss client can both connect to the log tablet, the tablet server, and the KV server. Oh, okay. It's basically the exact same thing. Yeah. I mean, the process is exactly the same. Either you want to connect to the KV or the log tablet. Okay. I understand. Of course, this is usually within the Fling source API architecture of split enumeration and split routers. Okay, so all of this is within this abstracted way with the what is it? The Fling API, Fling source API. Oh yeah, okay, that's understandable. And then what else? Okay, let's see the illustration here. Oh man, this is actually really helpful. If you want to read understand what the average was, all of this you probably wouldn't see this illustration on the Apache Fluss documentation itself. So this one is really helpful. Okay, so this is Fling source API. And the difference between log table and primary key table source are highlighted in green. Yeah, so Fluss table server and highlighted in green. The difference between lock table and primary key table source are highlighted. This is different. Job managers play enumerator. This is within the fling. Plus and fling as the Fluss coordinator. Okay. Give me all this thing plus snapshot files. Difference. Oh, okay. This primary key table is the one that highlighted in green. Okay. And blah blah blah. This is the same thing. Hybrid split snapshot plus log template. And then this one plus client snapshot file is the rocksdb snapshot file. Okay. Well, Flink provides the hybrid source abstraction that allows for reading from bounded source until completion, then switching to an unbounded source. Fluss has chosen to implement this within the split abstraction itself. I wonder what actually split abstraction is. Is it like class or 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 an API, or I'm thinking it's like a class that you can plug in into the Flink. I think it is. I have no idea what actually it is. Split editor. Yeah, I mentioned because this one mentioned that Fluss has chosen to implement this within the split abstraction itself. What's the difference? Why would you have split abstraction and hybrid source abstraction? Why there are multiple abstractions? For tablet buckets that are PK based, okay, the split enumerator also requires the metadata of the KV snapshot from the coordinator. KV snapshot is the rocksdb snapshot, right? Rocksdb snapshot, right? Yeah. It creates hybrid splits between which contain the snapshot and the log tablet. Okay. For hybrid splits, the H split reader, this one, this, first loads the bounded snapshot into rocksdb instance. What is bounded snapshot into rocksdb instance? I thought the rocksdb instance is like oh okay. I think what you mean is like load the snapshot file into rocksdb instance, like an actual instance process, not a process. Yeah, instance in your code instance object, and process the records, then switches to the unbounded log table, the change log. Yeah, okay, it makes sense. Schema management. Schema evolution is listed under roadmap. Let's take a look at the roadmap. Oh, okay, that's really interesting. Suppose complex array 0 this. Where is it? Where is it? Schema evolution. Where? It doesn't mention schema. Oh. Okay, that's very nice. Okay, Fluss coordinators. Fluss coordinators play a key role in the following functions. Regular cluster metadata. Yeah, basically the state of the entire system. Right. The states, the meta states. Internal theory, metadata, and coordination. What are you referring to by internal? There are multiple multiple tiering happens in the cluster itself. Which part are you referring to? The internal? Is it the tablet, the KV, or the lock part, or is it both? I think it's both. Like host steering coordination. Yeah, we haven't reached this part. Surfing method to track little clients. Yes, this one. Basically. Hey, give me everything. Oh, okay, here you go. So it's the plus coordinator. Okay. Quite simple. No. Yeah, quite simple. The coordinator is not really doing the weight heavy lifting. Okay, Fluss House architecture. I don't know why it has its own section. Maybe it's quite complicated. Let's see. Before we begin, let's define some terms to make the discussion more precise. These are terms that only exist in this post to make explaining things easier. The Fluss project does not define these abstractions. Logical table, block primary key, partition, and bucket. Fluss table served by Fluss cluster stored on disk and internally paired segment flash snapshot files. Lakehouse table, a payment table, says we're coming soon. Yay. Fed by Lakehouse peering. Logical table maps onto a Fluss table hosted by Fluss cluster. So logical table, this is basically what we have read before. Fluss table, Lakehouse table. Yeah, this one is the log thing and the KP thing and Lakehouse. Okay. Okay. Plus a set of client side and server side components, with Lakehouse integration being predominantly client side. Why? Why Lakehouse integration is I don't know. I don't understand why. Hmm. Lakehouse integration being predominantly client side. I don't know why. I think I think Lakehouse integration also server heavy too. I don't know. We can break up Lakehouse integration into the following pieces, which are somewhat interrelated. Lakehouse steering, basically copying the Fluss tables into Lakehouse table. Okay, from here to here. Okay. Storage unification, unifying historical Lakehouse data with real-time Fluss tablet server data. For real-time Fluss tablet server data. Yeah, somehow being able to read from both of this and this. Why we use it? Oh, okay. I think it gives the option for the client, for the user, to either, hey, do you have the lake house? Just plug in your own lake house. You can use Paymon or Iceberg or anything. Or if you don't have lake house, then feel free to use or object storage. Yeah, I think that's about it. The logical table could map to only Fluss table, or it could map to combination of Fluss table and Lakehouse table. It is possible for where to be overlap and therefore to duplication of Fluss table, Fluss and Lakehouse table. Okay. Yeah, makes sense. Unless you only want to read the historical part, I think you can just use Lakehouse table, isn't it? This is under assumption that to you want to do streaming. Yeah, real time plus. I mean, if you only want to historical data, you can take a look at the Lakehouse table without reading anything from the first one, or you still need the metadata to know where things are. So no, I think no. Lakehouse Iceberg, it's mapped into an actual tables. You don't need extra metadata to read from Iceberg. I mean, you still read from your catalog, but it's not within the Fluss. So yeah, Lakehouse steering, as with internal tiering, only log tables, and the change log of primary key tables can be tiered to lakehouse. Yeah, basically it does not include the kv thing. Okay, only tables and the change log of primary key tables can be tiered. Okay, understand. Payment itself converts the change log stream back into a primary key table. Why? Why? Okay, right now Apache Payment is the main open table format that is supported um, due to its superior stream engagement support, but Apache Iceberg integration is on the way. Lakehouse tiering is driven by one or more Flink jobs that use client-side Fluss libraries to learn what the tables must be tiered. Learn of what tables must be tiered. Yeah, Fluss coordinate. Sorry, I don't understand. What table must be tiered? Is it Okay, let's go on. I have a question. Do the tiering from read from Fluss table right to lakehouse table notify the coordinators of the tiering task completion or failure and metadata regarding lakehouse snapshot metadata and how it maps to Fluss table offset metadata. Fling lakehouse steering job. Fling plus Fling module. So this is within the Fling, right? It's like external coordinator job by the Fling itself. Fluss client, coordinator gateway, Fluss lakehouse API. Oh, okay. Read the Fluss table, the Fluss client, okay. A tiered log segment or tablet server, get the data, get an update table, peering task, okay. So, okay, this is quite interesting. I mean, like, tiering tasks, I thought it's supposed to be like internal to the Fluss, but uh, the state of the tiering itself can be mutated by the client, which is normally I don't like it, but okay, this is the way it is. Get and commit lake snapshot metadata. Okay, so this is very heavy. The logic is very heavy on the client. Okay, Fluss lakehouse API write lakehouse table. So maybe like it gets the data from here. So the coordinator gateway. I don't know why the coordinator gateway has I don't know. Is it the interface itself? Like why don't we just use the client to access everything? I don't know. But yeah, and then this one is understandable because this is different system. But this one, why we have single? Why don't we have a single interface to the Fluss cluster? Yeah. Anyway, it's going to get the data from here and write the data to here. Yeah, it just moves the data around. It just moves the data around. Which one I do not understand? This one. Why it has to ask which table must be tiered. Okay, let's go on. A table tiering task is initiated by lakehouse tiering process run in Flink. Okay, sending a heartbeat to the coordinator, telling it that it needs work. Okay, so asking a job from the coordinator. Hey, give me a job. The coordinator will provide it a table that needs tiering, which includes the metadata about the current lakehouse snapshot, including the log offset of every table bucket that the lakehouse snapshot corresponds to. Every table bucket. Is it the packet that was referred by the log table, like within the log table? It's okay. The lakehouse snapshot corresponds to lakehouse snapshot responds to. I don't know. I don't really know like how every table bucket. What is table bucket? Is it that one? Uh, is it this one? Let me see. Hmm. Mm, mm, mm. I see share table bucket. Oh, this one. Sorry. This one. Is it this one? Each table bucket is basically stored by a replicated log tablet. Yeah, this one. Basically, it represents a single file. But yeah, it represents a single file. It represents a single file. So where I was. Um. Okay. Wait. Sit here. The kind of log offset of every table bucket that lake house snapshot corresponds to. What is lake house snapshot? What does it look like? Is it like just I know iceberg. It doesn't always it's not always Paymon, right? It could be iceberg. Iceberg is basically just normal table. And the table bucket could represents um multiple table bucket could, if I understand correctly, multiple table buckets could represent like single table. So how do you map that? Yeah, I quite not sure. The tiering task will start reading from each table bucket from this offset. Hmm, let me see. What is the direction here? So the Fluss coordinator, it should be on fling. The Fluss coordinator anyway. Oh, this one is fling. Okay, this entire box is fling. Source enumerator asks which one. So the source enumerator asks which table can we read? Can I read? Learn starting offset of each table bucket. Okay, okay, and then it sends it sends it sends these the plan where should the source reader reads from sing writer, and then it asks the sing writer. I don't know why we have sing source reader and sing writer. See this one. Okay, read the table server, Fluss table server. Okay, and it sends to here and writes to the lake house, and it commits to here and once it clean committed, it writes the metadata to the lake house. Okay, and then it notifies the tiering task is complete. Now what's so complicated? The tiering read process reads aka log scan from the first table, which is this one here. From the first table is essentially the same as described in the log table and primary key table section in the Fluss core architecture section. The tiering read process. Where's the tiering read? Yeah, okay. For log tables, the table bucket are assigned as splits to the various source reader. This one table bucket. So one reader could read one bucket, or yeah, it's split that way. which use Fluss client to read the log tablet of each table bucket. I forgot the log tablet of each table bucket. Table bucket logically is mapped to a single log tablet anyway. But yeah, it's still true. I understand this word. Okay. Under the hood, Fluss client fetches from tablet server the leader replica of each log tablet, which may return data payload of tiered log segment metadata to the client. For primary key tables, the tiering job scans the changelog, generating hybrid split and assigning them to the readers. The Fluss client in each reader. Okay, the Fluss client could be multiple reader. Okay. We'll start by downloading the KV snapshot files or rocksdb and iterate over the rocksdb table, and then we'll switch to fetching from the changelog log tablet. Okay, it's basically the same process. Wait. Tiering read process. Why the tiering read needs to be this complicated? That's great. Wait, I lock scan. So wait, I'm sorry, I don't really quite understand. I'm not quite understand. Why? This is the exact same way previously being explained, but what was that for? Is that for the storage unification things? It's also for Fluss client for Fling. Okay, I know. It is for sorry, I forgot. I completely forgot. This is for that was for the previous one, the explanation of log scan. It's for Fluss client. Okay. Just normal Fluss client if you want to read from the string. But this one is the same thing basically, but the client writes to the lakehouse. Yeah. Okay. Instead of like the client reading the string. The tiering write process involving writing records as data files to lakehouse using Python or iFrog libraries. Okay, makes sense. The specifics are not important here, but the write pace requires an atomic commit, so newly written but not committed files are not part of stable yet. The tiering commit process involves the payment commit, but also updates the Fluss coordinator with the committed lakehouse snapshot metadata and the last tiered offset of each table bucket of Fluss table. Basically, we need coordination to ensure that tiering does not skip or duplicate, and the client can know the switchover point from lakehouse to Fluss cluster. The coordinators in turn notify the tablet server of the lakehouse offset of its table bucket, which is wait, sorry, let me repeat again. The coordinators in turn notify the tablet server of the lakehouse offset of its table bucket, which is the key part of storage unification story. So the coordinator basically tell the tablet server, hey, this is the last offset that has been written to lakehouse, so you can delete everything before that. Yeah. Okay. The Flink topology itself is very standard for writing to a lakehouse with multiple reader tasks. Anything records for multiple payment writer tasks with a single payment committer task that commits the writes serially to wait for multiple payments with a single payment committer. Oh, multiple writer, multiple reader, multiple writer, single committer that writes serially to avoid commit conflicts. There is one writer per payment bucket, and it seems plausible that the payment table partitioning and bucketing will match Fluss. So I didn't get around to confirming that. Yeah, basically it could be. And logically the it's quite possible because the single bucket is uh the unit of concurrency. So in Fluss, yeah, in Fluss, single bucket is the smallest unit of concurrency. So you can only so it is split into multiple buckets such that it can be read or written together concurrently. Yeah. Its logical table has a simple state machine that governs when it can be tiered. Tiered job finish new, scheduled, it can be pending, and on process called tiering. When it's tiering, it's failed, it goes back to pending. If it's done, tiering job finish, tiered job, then scheduled. So it tells, oh, okay, a tiering job has been done. So anyone come here and let me schedule you. That's basically it. Okay, I hope this is the last part almost. Client stitching including the lake house. The key to storage unification in Fluss is compatibility of the different storage formats and the work of the client to stitch data from different storage and different storage formats together transparently under a simple API. This is like the unification thing. Transparency under simple API. So basically, if I get the idea correctly, so you have a nice a nice interface where you can so basically the client does not really need to know what happens. It just okay, I want to read this table. So the client behind the scene just unify everything from the download from the lakehouse part, and once the offset has completed, then it switches to the RocksDB to the main tablet server. So yeah, this job of stitching the different storage together is shared across the Fluss client and Fluss Flink module. I'm sorry. Fluss, what's the difference between? No, I know what's the difference, but isn't Fluss Flink module uses Fluss client internally? I don't know. Look at this. Yeah, this is exactly what I'm talking about. Fluss Flink uses Fluss client. Unify on this with tiered log segments. Okay, Fluss client only tiered this part. It doesn't really touch the lakehouse part. Okay, the lakehouse thing is exclusively to be accessed by the Fluss Flink. I don't know. I would personally prefer that Fluss client also take care of the Fluss Lakehouse because this is quite confusing. I mean, yeah, this way you have smaller size Fluss client. You don't have to include the lakehouse capabilities if you won't ever use it, but I think it's not very, doesn't hurt to have the lakehouse API capability to be able to be accessed from the Fluss client itself. I don't know. I don't know, just my thought. Oh, okay, this is really good. The article is really good. Okay, let's go to the story unification. Is lakehouse tiering shared tiering? What is shared tiering? So far, I've avoided tackling this question. Fluss makes for an interesting case study. It uses two types of tiering. Tiering of Fluss storage, the long statement to object storage, formed by tablet server. This is classic internal tiering, which yeah, I only exposed with this kind of internal things should should happen behind the scene. The client should not be exposed to this. But the second one is tiering of Fluss storage to the lakehouse performed by Flink using Fluss client side modules and coordinated by Fluss coordinator. Yeah, I mean, you done your own thing. You don't imagine if I don't know if this. Yeah, I have mentioned this before. Like, why would coordinator being the state can be mutated by the client side? It's yeah, interesting design choice, I would say. In my first pass, I equated lakehouse tiering to shared tiering as described in my was a conceptual model for storage unification. In that post, I expressed reservation about the risk and complexity of shared tiering in general. The risk and complexity of shared tiering. What is it? I should read this later. My reservation comes from the complexity of using a secondary storage format to store the majority of the primary system's data. What is secondary storage format? Is it the iceberg, the lakehouse is secondary storage format? Sorry, what is shared tiering again? It doesn't explain it. Let's wait, I want to know what is shared. Okay, it explains. Shared tiering is data tiering where one or more data tiers is shared between multiple systems. The result is a tiering materialization hybrid serving both purposes. Tiering to lakehouse is an example of shared tiering. Uh, Secondary systems such as lakehouse compute engine. Okay. Um, One or more data tiers is shared between multiple systems. Does that basically mean there are two different systems that writes and read to the same tier, same data store? Shared tiering. Where is this one? Internal tiering, yeah, within the internal itself. This is what's this one? Materializing. Primary storage materialized to the secondary storage. And the secondary system can read from it. And this one is it writes to the long-term tier. Okay. Then write the first one. Secondary system. In Fluss, there's no such thing as secondary system. Uh, I don't know. It's my reservation comes from the complexity of using secondary storage format to store the majority of primary systems data, and the problem of performance due to not being able to optimize secondary storage for both primary and secondary systems. I don't understand what kind of optimization that you want, like compaction or I don't know. But soon, but I soon realized that Fluss lakehouse tiering is another form of internal tiering, as both storage tiers, which is the internal on disk thing, serve the same analytical workload and the same compute engine. Okay, and the same compute engine. A Fluss cluster is akin to a durable distributed cache in front of Paymon. Yeah, yeah. Where Fling reads and writes hot data from or to this durable distributed cache and reads code data from Paymon. Together, both storage types form the primary storage. Uh, the payment table only needs to support analytical workloads, and that can make full use of the various table organization options in Paymon without penalizing another system. Wait, I don't understand. The payment table only needs to support analytical workloads. So yeah, so it doesn't really need to support the streaming part, if I understand it correctly. And thus can make full use of various table organization options in Paymon without penalizing another system. So you mean like you can organize the data in Paymon in certain way that if you do not use Fluss, the streaming will be slow. A Fling directly writes to or reads Paymon if the organization table is in certain way that it optimized for analytical workload, maybe the streaming could be slower. The Flings could not optimize uh, its its streaming part. So yeah, I if that's what I understand from this part. Additionally, the logical data of the Fluss API is extremely close to both Fling and Paimon by design, which reduces the cost and risk associated with the conversion formats. What does that mean? The logical data model. Um, at the Fluss primary storage. You mean like the logically the data model the same way, like it based on change log and other stuff. Yeah, maybe that's it. Plus cluster storage and primary storage form the primary storage for the primary system. So this one, both Paimon plus it act as a primary store for the Fling. Okay. This is very different to Kafka architecture that might adhere to a lakehouse format. Kafka serve even strings largely in event-driven architectures, and Paimon serve as an analytical table. The two workloads are completely different. Sequential versus analytical. Yeah, I mean, sequential. Yeah, it's even you pan auditing. You write to the Kafka in the high frequency manner versus analytical, like one of analytical query. Having Kafka place the majority of its data in a lakehouse table would present many of the issues of shared tiering discussed in my storage unification blog post, namely conversion risks, converting from the yeah row base to columnar if I is it, and performance constraint due to using the same storage for completely different access pattern. Yeah, I'm sorry. Uh, Same storage for completely different access pattern. Uh, what's the? Oh, you mean like? Yeah, I mean, if I understand correctly, the Kafka here is in reference to using Kafka as the storage for Flame, and if you want to unify both, it's harder because it kind of expect that, if I understand correctly, when you want to store in the lakehouse, you want to store it in columnar format, and you cannot do that. You can do that. You can in Kafka you can the tiering part to the lakehouse you can convert it into Parquet or any columnar format, but when the when the Fling reads directly from Kafka as the changelog, as yeah as a streaming storage, then if you want to unify from both, you can do that, but the client would have to work even harder to unify it. It's a completely different storage format, storage system, storage format. Yeah, that's what I understand. Likewise, Kafka is unopinionated regarding payloads, with many being schemaless or using any one of Afro, Verbal, JSON, and JSON schema. Payload can be arbitrarily nested in any of the above formats. Yeah, true. Complicating the bidirectional conversion between lake host formats, which is Parquet or what is Parquet or Pine or Pine. Can you use payment to tier Kafka? I don't know. Or yeah, or any kind of columnar format and Kafka payload. Yeah, basically the what exactly I understand. Lifecycle management of the different tiers. As I noted on the last subsection, lakehouse tier is a form of internal tiering, as the lakehouse tier serves the same workload and the compute engine. Of course, the payment table could be read by other systems too, so there is still room for some conflicting requirement around data organization, but far less between a purely sequential workload like Kafka and analytical workload. However, curiously, Fluss now has two types of internal tiering. Tiering of the log segment file as is. This is the direct access form of tiering discussed in my conceptual module post. I haven't read this one. I should have read this one first. And tiering of log data in its logical form, which is of the API, which is of the API access form of tiering. I don't understand. I understand this one. Tiering the log data in its logical form. Oh. Okay. So tiering log segment basically like copying the actual file, like the copying the actual file. It is not copying the actual file. The tiering is based on offset. I assume the tiering is in logical form. I haven't read the. I should have read this one. Tiering the segment as is. No, if I understand correctly, the thing that being explained in this post is actually a logical form tiering, not the logical segment files. Um, but yeah, the question is why does Fluss? Oh, well, no. Oh, I think. Oh, okay. Hmm. Which is an API access form of tiering. I don't understand what is meant by API access form. Oh, okay, I remember. I think the segment tiering is uh this segment tiering. Hmm. Tiered segment. Yeah, this one. Replicated segments will stable. So yeah, segment the segment file is an actual file. This where's the segment? Where's the segment? Segment. File storage can post down file don't upgrade the tiers. The storage which enforce paper scheme. Okay, I cannot really tell. I can't really remember which part it explains that the the segment is like the one that being tiered. If I remember correctly, it has to read the actual data from the tablet server, the actual data, and like the offset is it is playing the offset. That way, it has to actually read the actual file, the data, logically, not just hey, can I copy the entire segment? Like, this segment is offset from offset 1 to 10. I will copy everything this file has. I don't think it works that way. I'm thinking like the log packet could consist of multiple segments, and then maybe maybe I don't know, the segment, the tiering one can the tiering job can be like, hi, I want to start the tiering from the middle up until a certain length, or from the middle all the way to the start, so like it's like just tiering the half of the tablet. I don't know if that possible. I don't know if that possible. I can't remember it explains this stuff. So yeah, okay, let's continue. The question is, why does Fluss need both, and why are they not lifecycle link? What does it mean by lifecycle link? Fluss table storage is expired based on a TTL, time to live, and each lakehouse format provides TTL functionality too. Tables from expired based on TTL. Table storage, I can really remember what exactly is the table storage expiry policy. But data is not expired in Fluss storage once it has been copied to Lakehouse. Yeah, it's not. Yeah, I quite not very sure about this one. I mean, I remember if the coordinator tells the tablet server that it has, or is it the opposite? The tablet server tells the coordinator that it has completed the tiering until a certain point, and then feel free to delete that kind of things. I don't know, is it like deleted based on the TTL or based on confirmation after the tiering has completed? First of all, I'm sure that linking the lifecycle of Fluss table and Lakehouse table data will eventually be implemented. Linking the lifecycle. You mean like lifecycle link? Oh, okay. So it's based on TTL instead of based on the thing that I just mentioned. Okay, yeah, it's not pretty trivial. It might be more reliable to keep. So I mean, like this way, if it's not being linked like this, there could be like overlap where, yeah, some of the data has been tier to the lakehouse, but it is actually still available on the install. I think it's not. Yeah, it's trivial, but it's not harmful either. It might be more reliable to keep internal lock segment tiering also, despite also using lakehouse tiering. Should the lakehouse become unavailable for a period. For example, when write availability of Fluss would be tightly linked to the availability of the lakehouse catalog without internal tiering acting as an effective spillover for staging mechanism. Without internal tiering acting as okay. Yeah, it might be more reliable. Yeah, it just okay. This one is more. It's personal thought from Jack. Yeah, but that would be that means you duplicate the entire thing, which is expensive, isn't it? I'm thinking, why can't you just tier? No, why can't you just copy directly from the object store of its internal tiering to the lakehouse? Why it has to going up the stack and go down again, like this one. It writes yeah, it writes from somewhere, okay, to the plus, and it tiered to this one, tiered log segment. No, this is not very good example. Tiering the object store. Yeah, okay. It writes somewhere. It writes from, I don't know, from Kafka, and then writes to plus, and then it being tiered to this tiered segment. And if I want to also tier to the lakehouse, it has to go up to the Fluss API and go here. Why don't we just copy it directly from this tier log segment to the payment table or to the lakehouse or anything? That way it doesn't have to do the expensive unification thing here. If the lakehouse main, I don't know if the object store here is like, yeah, I mean that's just completely insane, because this is not only copying it's not just copying it dumbly. There could be like some stitching logic where makes the data more presentable as an analytical store. Yeah, okay, that makes sense. Okay, yeah, that makes sense. But yeah, yeah, it could be expensive though, because you literally double the storage without lifecycle linked tiers. Like host tiering actually has more in common with materialization, data copy, not move. Yeah, okay. This is not a bad thing. There are cases where it might be advantageous to keep the life cycle of tiered lock segment separate from that of the lakehouse. For example, Fluss clients may wish to consume log tables in a purely sequential fashion and might benefit from reading tiered log segment. Uh, Wait, sorry, I don't understand. This is not a bad thing. There are cases where it might be advantageous to keep the life cycle of tiered log segments separate from the lakehouse. Tiered log segment from the lakehouse. For example, some Plus client might wish to consume log tables in pure sequential fashion and might be benefit from reading tiered log segment. Okay. So wait, the tiered log segment is sequential data, and the payment table has been written in certain way, so it is optimized for analytical stuff. Okay. Yeah, maybe. Yeah, okay, that makes sense. I mean, if even if it is being linked without link, even if it is being linked tiers, like linked to the lake house with the internal tiering, you still can do that, right? Or not? You can still do that. I mean, I think this is just continuation of the second option, the second opinion. Uh, without I need to read this part. I but I don't understand, like, consume the log table in pure sequential fashion. I mean, it assumes that the log the object storage tier and the lake house are still up. We have both. Like, it is the continuation of this point where Jack wants to have both the log segment tiering and the lake house tiering. That way you can still do this. Okay. Fluss also places Kafka API support on the roadmap, which makes maintaining internal tiering and lakehouse integration and lakehouse tiering as separately lifecycle managed process compelling, as it avoids the issues of conversion and performance optimization constraints. What does it mean? What does that mean? Plus also places Kafka API support. Is it like Kafka API support? It can Kafka API. Is it plus reading from Kafka with is there a Kafka here? Kafka. No, it's not on roadmap. Which makes maintaining internal tiering and lakehouse tiering as separate lifecycle managed processing as it avoids issue of compression. Kafka clients could be served from internally tiered log segment. Okay. And Flink Kafka client could be served and Flink could continue to merge both Fluss table and lakehouse table data, thereby avoiding the pitfalls of shared tiering as the lakehouse still only must support one master. This is another case where lakehouse tiering start looking more like materialization when using Fluss as a Kafka compatible system. I don't understand this 4 point. Fluss also plays Kafka API. Where is it? Kafka, is it Fluss accepting Kafka events or Fluss committing something to Kafka? Kafka client could be served from internally tiered log segment. So you are from Kafka. Oh, okay, I see. So, oh, okay, so I understand. Which make maintaining internal tiering and lakehouse tiering separately as. Oh, okay. So basically, Kafka client. So from internally tiered log segment, you push your event to Kafka, and Flink continue to merge both Fluss and table house. Okay, and Fluss and Flink just do its own thing. Thereby, table and log tiering. Flink continue to merge both Fluss table and lakehouse table data. Therefore, thereby avoiding the pitfalls of shared tiering, as lakehouse only must support one client. For issue of conversion and performance. If I understand partly that the Fluss can send events to log internally tiered segment, basically the sequential events from the log to the Kafka, and who is going to subscribe that? And Flink could continue to merge both Fluss table and lakehouse table data. Okay, sorry, I don't understand first. Yeah, I understand that the tool is going to commit the events to Kafka, and then what? Who's going to subscribe to that? Framework could continue to merge both plus and table, and therefore avoiding pitfall of shared tiering as the lakehouse. Still only master prop one master. So the lakehouse or the payment accept the data from Kafka, and then if and then the plane will read from there. So that way, Flink Fluss does not need to Flink does not need to tier the data to lakehouse, isn't it? Let's try to plus Kafka plus um where is there any way? Mm, no, okay. There's nothing on the internet. Can be confusing having two types of tiering, but it also allows for users to configure Fluss to support different workloads. If Fluss is only a lakehouse real-time layer, then it might make sense to only use lakehouse tiering. However, if Fluss need to support different access pattern for the same data, different access pattern, I mean accessing to yeah the one that I explained it before. This is this one like different access pattern. It makes sense to then it makes sense to use both using materialization port. Yeah, next time I should read the unification storage stuff. Oh, okay, quite long. Wrap up. Apache Fluss can be seen as a realization that Apache PyMod, while well suited to streaming ingestion and materialized views, is not sufficient as the sole table storage engine for Flink. PyMod remains a strong option for large-scale object store tables, but it falls short when low latency streaming processing require efficient changelog and high throughput small writes to the table storage. Fluss is designed to fill this gap. It provides the low latency tier with append only and primary key tables, support efficient changelog generation, and integrates with Pymon to through tiering. Client-side modules in Flink then stitch these tiers together, giving a unified view of real-time and historical data. Fluss aims to broaden its support to include other analytics engines such as Apache Spark, where wait, I saw Spark here. Oh, so Spark sub support streaming support union rates for Spark. Oh, okay. So you mean like right now it can only read from the Flink Plus client. Now it wants to get support for Spark, Trino, and Star. Okay. Oh, interesting. Another table format says such as Iceberg, making it more generic real-time layer for lakehouses. It should probably eventually be seen as an extension to Paymon more than a table search engine made specifically for Flink. Hmm. What stands out about Plus is how it shifts between tiering and materialization depending on its role. As a real-time layer in front of Lakehouse, it functions more like a tiering system since both Plus Cluster and Lakehouse serve the same analytical workload. If eventually it extends to support the Kafka API as the event streaming system, It would resemble a materialization approach instead. Fluss still faces several adoption challenges. Schema evolution is not yet supported, and lifecycle management remains limited to simple TTL-based policies rather than being tied to the lakehouse during progress. Its replication-based design also inherits the same networking cost concern that Kafka faces in cloud environments. What is the Kafka networking cost? I don't know. Isn't networking costs in Kafka? I don't know. I don't understand how it's even a thing. I mean, networking replication costs, whatever it is in Kafka, in anything, if it's like on different network, maybe it's like on different data center on different availability zone, it would be still very expensive. Let's copy it and playing 2.0 disaggregated state storage solve the large state problem without not working costs. But the state remains private to the Flink job. Fluss has placed the direct to object storage rights on its roadmap, so should eventually close this problem for workload with high networking costs. Directly rights to object storage. Okay. Oh, you mean like there would be no more these crazy lock replication things so that you can write directly to the object storage. And that was going to be very expensive. I don't know. Finally, given that Fluss copies heavily from Kafka for its log tablet storage, it raises questions for the Kafka community as well. Features such as columnar storage, projection pushdown, and stronger integration of schemas are all central to how Fluss turn a sharded log into a append-only table. While Kafka has traditionally remained unopinionated about payloads, there are benefits to adding schema-aware storage. It may be worth considering whether some of these ideas have a place in Kafka's future too. Okay, that's crazy. Okay, yeah. So that's all about it. Uh, I have quite understanding of the overview of the Apache Fluss itself. It's crazy. It's crazy that how people can build such complicated things. Uh, you know, I don't even, I never even use Fling. Maybe next time I should stream like me trying Fling. Yeah. Okay. Anyway, let's finish this streaming. It's like 10:41 p.m. Okay. See you. Bye.